All right, so you've written some code and it needs more memory. It seems to just happen, right? Like magic. But what's really going on under the hood? Well, it turns out there's this incredible, complex dance happening between your program, the operating system, and the actual hardware. Today, we're going to take that journey, all the way from a single line of your code deep down into the kernel.
So let's kick things off with that one big question. Your program needs more memory. What happens next? Maybe you're calling malloc in C or, a list in your Python script suddenly needs to get bigger. Your app makes the request, and then what? I'll tell you this much. It's not as simple as just grabbing a free spot in RAM. The whole thing actually starts with a really powerful illusion.
And that illusion? It's called virtual memory. Honestly, this is the absolute cornerstone of how any modern multitasking operating system works. You could think of it like a brilliant magic trick that the OS is constantly playing on every single program running on your computer. So what is it? Well, the key word here, for sure, is illusion. Virtual memory is what lets the operating system completely separate a program's idea of memory from what's actually happening on the physical chips. So every single application is tricked into thinking it has this huge, private, perfectly organized playground of memory all to itself. But in reality, the physical RAM is this chaotic, shared space with bits and pieces of memory all over the place. And this quote just nails it. This is that abstraction in action. Your web browser has absolutely no clue where your text editor's memory is stored. And you know what? That's a good thing. It's physically prevented from messing with it. This is the secret sauce behind system stability. It's the reason why when one app crashes, it doesn't just take your entire computer down with it. That isolation is absolutely crucial.
Okay, so how does the OS pull off this magic trick? Well, it gives every single process its own private map. This is a really structured layout, and it's called the process address space. Let's break down what that map actually looks like. So here's the typical layout. You've got your text segment, which is just your executable code. That's fixed. Then you have the data NBSS segments for your global and static variables. Also fixed. But where all the action happens, where things get interesting, is in these two dynamic areas, the heap and the stack. The heap is for stuff you allocate on purpose, and the stack is for all your function calls and local variables. And here's where things get really clever. You see how they grow? The stack starts way up at the top of the memory space and grows downward every time you call a function. Meanwhile, the heap starts at the bottom and grows upward whenever you ask for more memory. They grow towards each other. It's such a brilliant design because it maximizes the free space between them, letting both the stack and the heap expand as much as they need to before they ever risk running into each other. Right? So let's talk about that moment when your program needs more dynamic memory. You're creating a new object or reading a big file. What you're really doing is asking to expand the heap. But here's the thing, a program can't just take memory. Nope. It has to formally ask the big boss, the kernel, for permission. And that formal request is called a system call. So how does it ask? Well, there are basically two main ways. The old school traditional way is a system call called break. You can think of break as just moving a fence. It pushes out the program break, which is just the end of the heap, making it bigger. Super simple, but kind of rigid. Then you've got the modern powerhouse, mmap. This is way more flexible. It can create totally new independent memory regions anywhere it wants. This is a game changer for handling big, separate chunks of memory. So which one does a call like malloc actually use? The answer is, it depends. Modern C libraries are pretty smart about this. They use a hybrid strategy. For little tiny memory requests, they'll just use the fast and simple break call. But the moment you ask for something bigger than this magic number, usually around 128 kilobytes, it switches over to the more powerful mmap. It's really the best of both worlds. You get speed for small allocations and serious flexibility for the big ones. Okay, so our program have officially asked for memory. Now we're diving deeper. We're leaving the world of our application, user space, and heading straight into the kernel's engine room. We're going to see how it actually manages the physical RAM chips. Now, the kernel's #1 tool for this job is something called the buddy system. Its whole reason for existing is to fight a huge problem called fragmentation. This is what happens when your free memory gets chopped up into all these tiny little useless pieces. Even if you have a ton of free space in total, if it's not in one continuous block, you can't use it. And for the kernel, which is managing the entire system's physical RAM, wasting memory is a big, big no-no. So how does it work? Well, the buddy system has one simple rule. It only ever works with blocks of memory that are a power of 2.
So let's say your program asks for 21 kilobytes. The allocator looks at that and goes, nope, gotta round that up to the next power of 2, which is 32 kilobytes. To get you that 32K block, it might have to take a big 256K block, split it in half into two 128K buddies. Then it takes one of those and splits it into two 64K buddies, and finally it splits one of those into two 32K buddies and hands one over to you. And when you're done, it does the exact same thing in reverse, merging those buddies back together to create bigger and bigger free blocks. Pretty neat, right? But wait, there's a catch. The buddy system is fantastic for big page-sized chunks of memory, but it's actually pretty wasteful for the thousands of tiny little things the kernel itself needs all the time. I'm talking about stuff like process information or file handles. Think about it. Allocating a whole 4 kilobyte page just to store a 200 byte object, that's super inefficient. This means we need another layer of optimization on top. And that's where the slab allocator comes in. So this guy sits right on top of the buddy system. What it does is it asks the buddy system for a big chunk of memory. That's a slab. And then it pre-carves that slab into lots of little perfectly sized, ready-to-go slots for common objects. It's basically a super fast cache for the kernel's own internal stuff. By having these objects pre-initialized and ready to go, it cuts way down on overhead and makes the whole system run a lot faster. All right, we've looked at all the different layers. So now, let's put it all together. Let's follow one single memory request on its complete journey, from the moment it's made all the way to getting the memory. Okay, here we go. Step 1. Your program calls malloc. Step 2, the C library, working behind the scenes, catches that call. It makes a decision. Is this a small request? Use break. Is it a big one? Use mmap. Step 3, the library makes the system call, and bam, we jump from user mode into kernel mode. Step 4, the kernel's buddy system gets to work, finding the physical pages of RAM we need. Step 5, and this is the magic part, the kernel updates your program's page tables, creating the link between the virtual address your program sees and the physical address on the RAM chip. And finally, step 6, a virtual address is handed back to your program, which can now use its shiny new memory, completely clueless about the incredible journey that just took place. So you see, it's not just one thing. It's this beautiful, multi-layered orchestration. You've got the hardware abstractions, the smart user space optimizations in the C library, and the deep, careful scheduling inside the kernel. Every single layer has a crucial part to play in this complex system that gets memory to our apps both safely and super efficiently. And the craziest part? This whole elegant dance happens millions of times a second, every single day, completely invisible to all of us. It really makes you stop and think, doesn't it? What other incredible hidden systems are out there, quietly powering our entire digital world? Makes you wonder what we should dive into next.